When you first look at the sprawling equations of fluid dynamics, it can be, well, pretty overwhelming. It's a common feeling for sure. But what if I told you that all that complex math is really just telling a very simple physical story? In this explainer, we're going to pull back that curtain on the governing equations and show you the intuitive ideas that are hiding in plain sight.
Okay, so let's just dive right in. To get started, we really need to get our heads around the two fundamental ways you can look at a fluid in motion. It's all about your point of view, really.
And this image just illustrates it perfectly. So on the left, that's the Eulerian view. I want you to picture yourself standing on that bridge. You're totally still, you're focused on a single point in space, and you're just watching the river flow past you. You're measuring things like velocity, pressure, all at that one fixed spot. Now, on the right, that's the Lagrangian view. You're not on the bridge anymore, you're in the canoe. You've picked out a specific little chunk of water, and you are flowing along with it, watching how it tumbles and stretches and rotates on its journey down the river.
That idea of riding in the canoe, of following one single piece of fluid, is incredibly powerful. But how in the world do we describe that with math?
Well, the answer is this thing right here, the substantial derivative, written as a big D over a big dt. Now I know, don't let the name intimidate you. All it really means is the rate of change of some property, let's say the temperature of that little chunk of water, from the perspective of the water itself. It's the change you would feel and measure if you were actually riding along inside it.
And this is how that math connects right back to our analogy. That big D over dt, that's our mathematical tool that lets us jump from the fixed bridge right into the moving canoe. So as this little cube of fluid travels along its path, its properties might change, right? It could heat up or get compressed. The substantial derivative is exactly what tracks those changes along its entire journey. So the substantial derivative tracks how properties change along the path. But what about the changes to the shape of the fluid element itself? Let's check out another mathematical tool that helps us visualize that.
This one's called divergence, written as del.v. Now, you've probably seen this in a vector calculus class and thought of it as just, a math operation. But in fluid dynamics, it has a very real, very physical meaning. It's literally measuring how fast a little piece of fluid is expanding or shrinking.
And this slide gives us the perfect mental image. Think of that red cube as a tiny, squishy box of air. See those red arrows pushing inwards? They represent forces that are squishing it. As the volume of that box gets smaller, we just say the fluid is being compressed, and in that case, the divergence would be a negative number. If the arrows were pointing out and the box was expanding, well, the divergence would be positive. It's a direct measure of compression or expansion. Simple as that.
So we've got these cool mathematical tools for tracking properties and watching volumes change. But what are the underlying physical rules they're actually enforcing? The answer is something you've actually known for years. All of that complexity you see, it all boils down to a foundation of just 3 super simple fundamental laws of physics. And here they are. First up, mass is conserved. You can't just create or destroy matter out of thin air. That's the whole principle of the balance scale. Second, good old Newton's second law, F equals m. This is what governs how the fluid moves and accelerates when forces act on it. And third, energy is conserved. It can change forms from heat to work to kinetic energy, but the grand total always stays the same. That's the first law of thermodynamics. And that's it. That's the whole foundation. These 3 rules are the entire bedrock of fluid dynamics.
Okay, let's tie this all together, because getting this next point is really the key to truly understanding the governing equations.
So here's the most crucial point, the big takeaway. Every complex equation in computational fluid dynamics is simply a mathematical restatement of those 3 rules. The continuity equation, that's just a fancy way of saying mass is conserved. The Navier-Stokes equations, that's just a very detailed, very specific version of F equals ma. And the energy equation, you guessed it, is a statement of energy conservation. So the math might look really difficult, but the physics behind it is actually pretty straightforward.
So I'll leave you with this question. The next time you're faced with a page full of derivatives and integrals trying to describe a fluid flow, are you just going to see the abstract symbols? Or are you going to see what's really there? A simple story of mass, momentum, and energy, all just trying to stay in balance.